Now, what about space-fed arrays? What do I mean by them? And here's a cartoon configuration that gives you a good picture. Because I'm going to show you some pictures of antennas, and you'd say, how does that work? Because when you see a picture of it, you say, huh? Anyway, a reflector array configuration consists of an offset feed where the radiation comes out, and you've got your curved phase from the offset feed, and it will feed into the phase shifters. These are little antennas which receive the transmitted signal that comes out to them. And then the signal that hits each phase shifter, and you can imagine these are rectangular arrays, or they're two-dimensional arrays of phase shifters. In either a rectangle or a circle. I'll show you pictures in a minute. All the phases are adjusted appropriately, and then the signal goes through, hits a short circuit, and is reflected back out with the phase all shifted in a direction to steer in this particular wavefront with a certain combination of phase shifters shifted appropriately. Okay? Now here we have a lens array where we have a lens, which in this case is on axis, but it could be off axis. But it's a lens array which sends a beam into phase shifter antennas, little antennas on each phase shifter, which phase shift appropriately, acting as a lens to converge the energy, and then transmit out a phase front after receiving steering instructions, changing the phase of the lens from the lens array. So we have reflector array configurations and lens array configurations for space-fed arrays. Now let's look at some pictures. And here's a picture of a lens space-fed array. It's called the Multiple Object Tracking Radar. And this picture I'll start with. Here you see a horn, and that horn would emit high-powered C-band energy out to this set of phase shifters, which receive the energy from the horn and have 8,192 phase shifters in that plane. This plane here. And that takes the place of a dielectric lens that is sometimes used. And the spherical wave of microwave energy is phase shifted appropriately to form a beam and point it in the desired direction. So what this does is this allows you to, and this has spacing properties so that you can scan simultaneously a large number of targets with one lens array in a general direction, but you can move where that's pointing around to different azimuths and elevations depending on where your targets are of interest. Now here are some lens arrays. The Patriot Radar, if you look back here, you can see it's space feed. And then it's the energy is received, phase shifted, and boing, out it goes. It is a lovely picture of the Russian SA-10 flap lid. In the Russian air defense system now, they call it the S-300. It's an X-band fire control radar, and it has phase shifters inside here, and here's its feed and the energy pointing in different directions. And you can see it's mobile, as Patriot is. And now here's a really neat system. This system is part of the S-300 air defense system that the Russians have. Its NATO designation is Big Bird, and it's in the SA-12 area. And what it has is it rotates mechanically in azimuth. And it has back-to-back 2 reflector rays. So here's a horn coming out, and you have an off-axis feed, which comes into this set of receiving antennas for each element, is phase shifted out, and in the front, I'll call it, a beam goes out, and you can not only track the beam mechanically or electronically. Well, excuse me, you can track it mechanically in azimuth and or electronically and mechanically in azimuth and in elevation. This says it more coherently. But it's got 2 systems back to back, which give it twice the rep rate on the targets. And this is the giant truck that's used to transport it. And here you see its front, and these are all from the web. It's amazing what's on the web. Oh, excuse me. This particular picture was taken at an air show, and it's I got it from the web from Martin Rosenkrantz. It's copyrighted from him, and I'm using it with his permission. I'd like to thank Martin very much for the use. But this particular one on the right, I got it from Wikimedia. It's in the public domain. Okay, so now what would be some configurations for constrained feeds, both parallel and series? Here, I mentioned how what you'd do is you'd have a set of phase shifters. This was all rotated to the side. And this is in a called a corporate parallel feed. And you'd change the phase linearly to have the beam go out. You'd add maybe some more phase to go in a certain direction. And you'd 2-to-1 power split a number of times to take all of the energy from the main transmitter. Or you could have the microwave power come in, and this is the architecture of an end-fed series feed, where the power comes in, goes out with no change in phase, you change it phi here, goes out, and then it's changed another phi, so it goes out 2 phi here, then 3 phi here, then 4 phi here. So these series and corporate feeds are different methods, and they have different pros and cons. And the insertion losses in the series feed are less than the parallel feed. Okay. Now on to frequency scanned antennas. Now frequency scanned antennas, I don't bring this up because I don't know of any frequency scanned antennas that are under development in the United States. But a lot of systems, an antenna system has a lifetime of 20 or 30 years. And in the past, people have built a lot of frequency scanned antennas, and they're on a lot of our different radar systems. So I want to explain what a frequency scanned antenna is. And here we have our old friend that the phase shift difference between 2 elements is 2 pi times the frequency of the radiation times the length divided by the velocity. And what you do is you just take the frequency and velocity out, change it to lambda, and you have the phase shift is inversely proportional to lambda, the length of the line connecting the various elements, and v is the velocity of propagation. So if you have a feed where you have an element and then the power comes out to that element with a certain phase and then goes through a length L, which will shift the phase an amount phi, it's transmitted out, and then it's passed on and comes out the third element with a shift twice phi, then 3 phi, 4 phi, 5 phi, 6 phi, and D, of course, is the separation. What you do is you get what's called a serpentine or a snake feed. Then there's a termination stub at the end. And by changing the frequency of the radiation, you'll change the frequency of the main beam, because you can change the phase shift. Neato. The beam steering in one direction has been implemented by changing the frequency of the radar in this case. Now for excursions of plus or minus theta 1, the wavelength change is given by this. And for a 45-degree angle of theta 1, 30% bandwidth is required for a D over L of 5 and 7% for a D over L of 20, where D would be the length of the spacing and L would be the feed. To see what this looks like, this is what these look like physically. A planar array where you'd have a phase shift here, and this is an above folded waveguide known as a snake feed or a serpentine feed. And this configuration is used to scan a pencil beam in elevation and a mechanical rotation provided in azimuth. The frequency of scan technique is well suited to scanning a beam or a number of beams in a single angle coordinate. Okay. Now here are two naval radars that have serpentine feeds. You can see them here. And the SPS-48E and the SPS-52 both have serpentine feeds. And this is built by ITT Gilfillan, and this is I'm not sure who it's built by, but it's the photos courtesy of the Navy. Now on to hybrid methods of scanning. The first one is really a neat one, and it's the ARSR-4. It's the radar that the FAA and the Air Force use for long-range detection of surveillance. And it's got stressing requirements because it needs to measure height. It has to have very low side lobe capability and all-weather capability with linear and circular polarization. And the antenna design, this particular neat antenna design, was enabled with the use of significant use of CAD and array tracing. And you can meet these requirements easily with a phased array, but Northrop Grumman designed this with an offset feed array. So it's a small feed. This piece in blue is actually this array, which is small in size, 23 rows and 34 columns, and it generates 10 elevation beams, and it meets the azimuth side lobe levels, and different numbers of these rows and columns will be illuminated, to generate the different transmit and receive beams. And I'd like to thank Frank Sanders for permission to use this photograph. When Westinghouse, what this contractor's with, was taken over by Northrop Grumman, and they got out of this business, the ARSR-4 business, a lot of photographs were lost. And I think this is the best photograph I could find anywhere, any place, that Frank, who works for the government, I believe, one of their organizations, it has of the feed of that antenna system, which is really it's a beautiful design, and some very nice papers have been put out on it in IEEE journals and proceedings. So let's now talk about phased array versus reflectors versus hybrids. We're getting now down towards the end, thank God. Phased arrays provide beam agility and flexity. Yeah, I drilled that into you enough. They're an effective resource management for multifunction capability. You can do nearly simultaneous track over a wide field of view, and you have the ability to adapt your pattern control. I haven't talked about that earlier. That's a neat thing about the phased arrays. Phased arrays are significantly more expensive than reflectors of the same power aperture, but you don't get all these functionality that you have above. If you need 360-degree coverage, phased arrays, you might need 3 or 4 filled phased arrays. There are larger component costs and longer design times than just reflector antennas. And hybrid antennas are often, it can be an excellent compromise. And the ARSR4 is just an excellent example, I think, of a lower cost reflector, combo reflector. It's a hybrid. And a 2-to-1 cost advantage over a planar array while providing very low azimuth side lobes. So I wanted to give you an idea. Everyone else is phased arrays, reflectors, taste great, less filling. This is, there's a lot to be said for those. Now on to some other antenna topics. If you remember back to Lecture 8 when I first brought up antennas, I showed you from Krauss's antenna book sort of a tree diagram of all the different kinds of antennas that you can make. And here's a circular patch, a linear array of circular patch antennas. Another kind, log periodic antennas. You build these because you want wide bandwidth. Spiral antennas. So there are all kinds of different antennas for certain kinds of specific applications. And what I've tried to do is to weight the time spent on the different kinds of antennas that are out in use and in development. But I wanted to show you that there are a lot of other printed antennas that are out there in the world. Okay, now on to antenna stabilization, which you might call other issues. If an antenna is on a ship, you're going to need servo mechanisms to control the antenna position to compensate automatically for the change in the antenna position of the vehicle that's carrying the antenna if the vehicle is moving, like a ship. The stabilization requires use of gyroscopes or GPS or a combination to measure the position of the antenna relative to the Earth, and radars which electronically scan, like Aegis, can compensate for beam motion by appropriately altering the beam steering commands to the radar's computer system, or antennas which are located on ships and have dishes need to have appropriately high torque ability of the azimuth and elevation mounts so that they can adjust in their control loops of their antenna adjustment to stay on the target that they're tracking in the air or above the air. And here are different, next on to the next issue, radomes. Radars are made for the most part of metal and stuff. Even phased arrays are covered with radomes, a radar covering. And for dish antennas, for the most part, radomes are used to protect the antennas from weather conditions such as wind, rain, and salt spray. Metal space frame techniques, which are used often for large antennas, typically have losses of about 0.5 dB. These need to be put into the radar equation. And inflatable radomes have also been used. They have less loss, but they got more maintenance, and they can flex in the wind. And if you have a hurricane, they won't have the mechanical abilities, say, of a metal frame space frame radome. You have to trade all that off. And here's a picture of there's dishes in these two different antennas, in these two different radomes. And of course you can imagine these dishes, referring to the previous view graph, have to have very strong mounts if this ship is operating in high seas. Now in summary, finally, the enabling technologies for phased array development have really been ferrite phase shifters, where we've got the switching times down to just a few microseconds, the order of magnitude, and low-cost monolithic microwave integrated circuit technology has been a big driver, and I'm going to talk about that when I talk about transmitters and receivers in detail. The attributes of phased arrays we've really gone over. They're inertialess, rapid steering, multiple independent beams. You can do adaptive processing, time-share, multifunctioning, and they're higher cost, much higher than other alternatives. Often, other antennas can offer cost-effective alternatives than these active phased array designs. Lens and reflect arrays are often used. Reflectors with small array feeds, etc., or mechanically rotating frequency scanned arrays, and we've gone over them. I'd like to acknowledge the great work that Pamela Evans and Alan Fenn have done, and they have earlier on in their career they have taught more advanced lectures in antennas that I have been lucky to go to and learn an awful lot about them. And a number of the view graphs in these two antenna talks were ones that I took from Skolnick and redesigned it, and then Dr. Evans got a hold of it, and she made it even better and better. But I wish I had 1/10 of the knowledge of this lady and gentleman that they have. They're real sharp cookies, and I've learned an awful lot of what I've been able to, I hope, explain to you from them. Books. Antennas, they're all over the place. We've got Skolnick's books, and I want to not forget another plug for Mark Richards et al., their elementary book. I haven't had the chance to read their antenna section. I'm sure it's a pretty darn good one, as it is an introductory book. But as you know, this is the train had left the station before I ever received a copy of the other book, and all of you graphs are pretty much made. And Merrill Skolnick's handbook, the 3rd edition. Belanis's book, utterly fantastic. If you go to grad school, most often you'll take an antenna course in a term or two, and it'll be out of his book. Krause's book that came out in 2002 is another fantastic book. And I've used, not Hansen so much, but it's got a lot, some I've used, but Malio's book on phased array antennas, his handbook, I learned a lot from his. And I took some stuff, and I referenced some stuff from Roger Sullivan's book on radar foundations, and a paper that Larry Corey gave in the IEEE press in its proceedings of an IEEE conference on phased array radar systems and technology. And 4 problems. We've got the one that's we've already mentioned to you, these problems from Skolnick, and for extra credit, do problem 9.40 in Skolnick. So I think that's the end.